Hello everyone, and thanks for tuning in. My name is Zvika Gift, and I would like to talk to you about a seemingly simple problem that arises in assembly planning. So our problem is, given a connected set A of unit grid squares, such as the example input here, we wish to find a subset S of A, a proper subset, that can be rigidly translated upwards to infinity, such that each of the sets S and its complement A minus S is connected, and also S does not collide with its complement throughout the motion. So let's look at a valid solution here. So the green set of squares is a valid choice for S because we may translate it upwards to infinity, and each of the sets that we have here is connected. On the other hand, this red set of squares is not a valid choice for S because the complement is not connected. We have these two connected components here. And finally, this is also a bad choice for S because we would have a collision between the red set of squares and the other square. This problem might seem a bit easy. So this is just a negative instance for you where there's no valid choice for S for you to ponder about it if you wish. So for the rest of this talk, I will be giving a background from assembly planning on how we got to this problem. I will discuss briefly some hardness results that we have, and then I will discuss positive results with a focus on a fixed parameter tractable algorithm for the problem I just presented. So the background. So an assembly A is a collection of non-overlapping parts. This is an example of assembly of polygons. And a subassembly, S of A, is a subset of the parts composing the assembly in their relative placements. In this talk, all the parts will be planar, since we're in 2D here. A two-handed assembly operation is a motion that merges two separated subassemblies into a new subassembly. And the motion, in our case, will be just a single translation, such as in the example here, where this subassembly just moves in one direction until it mates with the other subassembly. And in general, the problem in assembly planning is to find an assembly sequence, which is a sequence of assembly operations that merge separated parts into the final assembly. So here, for example, we have this assembly on the right, and on the left, we can see an assembly sequence for it consisting of single translations. And a common constraint is to have each subassembly that arises in the sequence to be connected, which is the case here. And the motivation for that is shown through this example where we have a subassembly on the right that is not connected. So in order to complete this operation, we would have to have some other hand holding one of these blue pieces, or maybe a fixture that would keep their relative position, and this is undesirable. So in practice, assembly plans rarely have such operations. And so this is a definition now that we'll be using a lot later. So given an assembly A partition is a subassembly S and a motion that allows moving S sufficiently far away from its complement. And we call a partition a connected partition if S and its complement are connected. And the problem that we'll be working here is called assembly partitioning, which is finding a partition, or more specifically, connected assembly partitioning, where we want a connected partition. And this problem arises in the assembly by disassembly approach to assembly planning, where we actually find a disassembly sequence and then reverse it in order to obtain the sequence that we want. So some previous results here on assembly partitioning, it was shown to be NP-hard for general motions or multiple translations, but it is solvable in polynomial time for single translations, such as in the examples I was showing. And then for connected assembly partitioning, we also have hardness results for the case of multiple translations. And then, given the polynomial time algorithms for single translations without the connectivity constraint, a natural question that was posed is what happens if we also require connectivity in this seemingly simple case. And this is the problem that we settle in this paper. And we show that it is NP-hard and also fixed parameter tractable for unit grid squares, which is the case that I presented in the beginning. And so that is the background. Now I would like to discuss the hardness results that we have. So here's a construction from the previous hardness results for connected assembly partitioning These were the most constrained previous results, and this construction admits a partition with a linear number of translations. And when I say that, I mean linear in the number of parts in the assembly. And we can also see that it has a lot of non-convex parts with forks and other similar structures. And our case is much more restricted in that we only allow a single translation in order to partition the assembly. And we're also restricted to unit grid squares. So we show that even under this restriction, the problem remains NP hard. We do that by reduction from a new planar SAT variant, which I will briefly describe. So I'll start talking about monotone planar 3-SAT, which is the known NP-complete 3-SAT variant. So by monotone, we mean that all the clauses are either positive, that is, they contain only positive literals, or they may only contain negative literals, such as the ones here below. And by planar, we mean that the formula can be drawn as follows. So we can place all the variables on a line where all the positive horizontal line, that is, with all the positive clauses above it and all the negative clauses below it. And we add an edge between each variable and clause whenever the variable appears in the clause. And we may draw this graph in a rectilinear embedding with no crossings. So this was known to be hard, and we additionally require each clause with 3 literals to have 2 neighboring variables. So what this means is 2 variables that are adjacent on the variable line, such as x5 and x6 here. And this instance that you can see here is actually satisfies this requirement. I'll give the outline for our reduction. I'll just give you a gist, a small taste of what we did. So we actually show hardness for connected partitioning for polygons. Then we adapt the construction for unit grid squares. So given phi, an instance of the planar SAT variant I just described, we construct an assembly A such that phi is satisfiable if and only if A has a connected partition for the positive y direction. So here we have phi, and this is how we translate it to an assembly. So the variables are translated to rectangles that are also placed on the line, horizontal line. And what this drawing represents is rectilinear polygons. So each line segment here is a very thin piece of a polygon. And the main idea is to assign a variable in phi to be true if and only if the corresponding rectangle goes up in the connected partition. So this is the correspondence that we have. And I will just briefly go over the clause gadgets that appear here for each clause. So if we have a clause with 2 variables, we have 2 parts for it, for the clause gadget. And these 2 parts touch the variables or the variable rectangles that correspond to the variables in the clause. And we need to have this property here that basically gives us a choice of what to do with the variables. So if, say, part A translates up, then B also has to translate up because B is blocking A here. And now since both A and B are translating up, in order to have a connected partition, they have to be connected somehow. So therefore, either xj or xk has to also translate up. And therefore, given that A translates up, the assignment that corresponds to the partition will satisfy the clause. And this basically creates an OR gate with 2 inputs. So we can generalize that for 3 variables by composing 2 OR gates. And we get a similar result where if A translates up, then one of these 3 variables also has to translate up, and the corresponding assignment would satisfy the clause. In this case, we have 4 parts in the clause gadget. And note that xk and xk plus 1 are the neighboring variables that each 3 clause must have. And we have some flexibility here in the partition in that it's possible for A and B to translate up while C and D can go down. And without going into the full details, it's important for us to have these variables be neighboring because we do not want to have any other clauses here between xk and xk plus 1 that might interfere with C and D going down. And this is, I'm just talking about positive clauses now. And by the way, we can also force part A to go up in any connected partition. So this is just a taste of the hardest reduction. And now that we're done with that, I'll talk about positive results. So from the problem I presented, so we give a 2 to the kn squared time connected partitioning algorithm. And in this case, k is the size of the partition, n is the number of squares. So this means that if we have a small number of squares that we can translate up such that we get a connected partition, we can find it quickly. So this means that the connected partitioning for unit grid squares is fixed parameter tractable. This means that the factor with the exponent only depends on k and not on n. And so if k is small or fixed, we actually get a polynomial time algorithm here. So this is the first result, which is our main result. And then we also have another result, which is a special type of grid square assemblies. We call it horizontally monotone, where we always have a connected partition, which can be found in linear time, which I will touch upon briefly. So I will just present some definitions. So blackboard X denotes the infinite grid of unit squares, and we represent a square in this grid by its center. It will be convenient to not make a distinction between a square and its center throughout. So for a grid square assembly, which is a finite subset of this infinite grid, the adjacency graph is a graph on the squares, where we have an edge between two squares if they are vertical or horizontal neighbors. So we cannot have diagonal edges in this graph. As shown here, it is basically a subgraph of the grid graph. And we say that A is connected if its adjacency graph is connected, which is also the case here. So now our problem, the parameterized version of our problem, is given a connected assembly of n unit grid squares and a parameter k. Is there a connected partition S star for the positive y direction, such that the size of S star is at most k? And instead of saying all of that, I will just call it a valid partition from now on. So for this example input that we saw in the beginning, provided that k is large enough, we get this partition here as star as an example. And our overall approach for this problem uses the following observation, which is for any partition S of A, there are two adjacent squares S and T such that S is in the partition, that is, S translates up, while T is not in the partition, so T does not translate up. And this is based on the fact that A is connected. Since A is initially connected, in any partition, we must break contact between some two adjacent squares. So we can consider all pairs of adjacent squares S and T in A, of which we have a linear number, and ask the following question for each of them instead. So this is a refined question where we say, is there a valid partition where also S is part of the partition S star and T does not belong to the partition? So by trying all the options, we will answer the original question. By the way, this is a slightly different approach from the paper where we only fixed S, and this just slightly simplifies things for us. So from now on, I will focus on the new question with a restriction of an S and T. The main idea is to grow a partition from S by alternating between the satisfaction of separability and connectivity. So we have two constraints that we have to satisfy, and we alternate between their satisfaction to add more and more squares and eventually get a partition, or to conclude that we do not actually have a valid partition. And to do that, we use a recursive procedure called augment. That answers a slightly more general question. So augment receives, in addition to T and K, receives the set subassembly S, and it determines whether there is a valid partition S star that contains S while not containing T. So for example, for this input here, with S as the green square, we would like to return a yes here because we can find there is a valid partition S star that contains S but not T. So to answer our question, which is based on just these two squares, we can call augment with just the square S as the set. And the way augment works is by branching at each call on at most two subassemblies S1 and S2. Each of these subassemblies properly contains S, so that is, at each step it must augment the set S, which is already assumed to be in the partition. And furthermore, with the additional property that for any valid partition S star that contains S, we must have also S1 be contained in it or S2 be contained in it. That is, we try two options such that one of them will recursively lead us to a valid partition if such a partition exists. So we'll go over an example to show how augment works. So we start with just one square as our set, big S. And the first thing that we do is we consider all the squares that might block the set subassembly big S. In this case, there are no such squares, and the set B is just the original square S. And then we do checks that are for the connectivity constraint. So first we check if A minus B is connected. And in this case, A minus B is not connected. We get two components, so the white one and then the blue one. And I'm not going into detail about this case because in this case we can always make one recursive call. In this case, we would just add the blue component to S because the other component contains T, and T must stay behind, so therefore we must add the blue squares to S, and we get this new set S, on which we apply augment recursively. So now we again have to check if there are any squares that block big S, and there are such squares, so we add them, and we call the resulting subassembly B. And this is a step that we obviously must do. If S must translate up, then obviously B must also translate up. In this case, when we do our checks, A minus B is connected. And now we get to the interesting case where B is not connected. And so this is really the heart of our algorithm. This is the interesting case. And in this case, if B is not connected, we use a sub-procedure called connect to identify the two subassemblies, or at most two subassemblies, that augment will recurse on. So in the example here, this is how the two subassemblies would look like. So we'd have S1, which is B augmented by this blue path, and S2 is B augmented by this other blue path. Also note that if we pass both of these checks, then B must be a valid partition. And we also check, it's not mentioned here, but we also check at any stage if we must include T, or if the size of the S or B is greater than K, in which case we just return false or a negative answer. So now we'll go into connect and how connect works. So connect gets, continuing with the example here, so connect, in addition to the assembly A, it gets a subassembly B, such that B can be translated upwards, but it is not actually connected. We have to figure out how to connect B somehow. So the way we do this, or the way connect does this, is by constructing a planar graph G, which you can see here. And it identifies one or two faces in G whose boundaries define S1 and S2. So if we remove the squares, this is what the graph would look like. The tricky part here is to find where exactly the faces are. What are exactly these two faces? So I will explain that now. So for that, we'll just need a few definitions here. So for a subset X of the infinite grid of unit squares, we define the shadow of X to be X plus all the squares that lie above X. So this is an infinite set here. So if in the example here, the crosses are X and all the dots are the squares that are above them. And here we also see the adjacency graph of the shadow of X. And we are interested in the boundary of this shadow, which is formally defined as the boundary of the unbounded face of the adjacency graph of the shadow, marked in blue here. And we will orient the boundary in the counterclockwise direction. We can think of them as the outer squares of the shadow here. And because we're working with B, we'll just set L to be the boundary of the shadow of B, LB. So let's see a few more definitions. So for B, we let B1 through BU be the connected components of the adjacency graph of B. So we have three such components here, B1, B2, and B3. And we take Z to be all the squares of B that lie on L. So for example, so there will be all the squares through which this blue path goes through. And we take Zi to be Bi intersected with Z. So that means, for example, for Z1, that's the squares of B1 that lie on L, which are highlighted here now. We can look at L in this representation where we draw it out on a line, and we draw the zi's according to the order in which they're encountered in the counterclockwise traversal of L. So first we encounter B1, then we encounter B2, rather Z2, and then Z3, and then Z2 again. And we notice that we have this nesting relationship between zi's along L, and we're interested in looking at the innermost zi. We would like to connect this innermost zi to some other component of B with the new squares that we're going to add. And so this is how we're going to do it. So this is B from before. So first we'll compute L, as shown here in blue, based on the shadow of B. And we would like to add all the squares along L from to this graph G that we're constructing from the first square of B that L encounters until the last square of B that it encounters in the clockwise traversal, including squares, grid squares that are not part of the assembly, such as these two points here. And we also add to this graph all the squares that are outside of B. And we find the adjacency graph of all these nodes, and we get a graph that looks like this. And now in this graph, let's look at the zi's. So in this case, we have the innermost zi here, consisting of two squares. And in order to find the faces we're interested in, we'll look at the edge along L in this graph that we just defined that precedes zi. So the first time we encounter the innermost zi, and we look at the face to its right, and the boundary of the face defines the nodes that we're going to be adding, or rather the squares that we're going to be adding to B in order to augment B and get S1. Similarly, we take another edge, this time the edge that is the edge that precedes Zi, the innermost Zi, and that defines, we look at the face in which it's contained, and we get another path of squares here that we can add to B, and that will result in S2. So these are the two options here. And now, for correctness, we just need to have at least one of S1 or S2 be defined, because these faces cannot always be bounded. So we must have one of them be bounded. And the correctness follows from S star from the following fact, where for any valid partition S star that contains B, we must have either S1 or S2 be contained in this valid partition S star. And this follows from planarity, in that the intuition is that we cannot take a shortcut and somehow cut through the face. And so that concludes the description of the augment procedure, which uses the connect sub procedure. So the running time of each call of augment takes a linear time. And since we make a binary choice at each step, and the length of each branch in the recursion is at most k, we get a 2 to the k n running time. And because we also have to go over all choices of S, T, and K, the total time required to find a valid partition is as follows. So we gain another factor of n here due to the choices of S and T. So now we're done with this. And another result that we had for a positive result is for a restricted case, where the intuition is to avoid interlocking hooks, such as the one from the negative example I showed you in the beginning. These hooks also show up in the hardness construction. And this is how we avoid them. So the definition of a horizontally monotone assembly is each square in the assembly has a rightward monotone path to some rightmost square in the assembly. So let's look at an example. So from this, so what is a rightward monotone path? It's a path where we can only go up, down, or right. So from this yellow square, we have a rightward monotone path to this rightmost square of the assembly. And we can also use the symmetric definition, just replace left with every time I said right. And so this guarantees that there are no interlocking hooks, because if we had an interlocking hook, like the example we just started with, well, then we would have this red square here from which we do not have a rightward monotone path to some rightmost square. So in order for it to be a horizontally monotone assembly, we would have to have a square, let's say here, and then this example would have a valid partition. And so for such assemblies, we can always have, there always exists a connected partition, and we can also find it in linear time by considering three possible cases. So some future work. So we're extending our fixed parameter tractable algorithm to general polygons rather than just unit grid squares. And through this process, we actually learned that it's not the shape of the individual parts that matters, but the shape of the union of the assembly when you consider it as a whole. That is what affects the complexity of the problem. So another thing we have to consider here is finding a complete assembly sequence, which is our original problem. Finding a valid connected partition does not guarantee that we can keep decomposing the resulting subassemblies while respecting the connectivity constraint. We might actually make a wrong move. Therefore, we still need to think about how to solve the problem of finding an assembly sequence under the connectivity constraint. And also, in our positive results, we heavily relied on planarity. So the question is, what can we say about any positive results for 3D? So thank you very much for listening to this talk. If you're interested in such problems, feel free to contact me.